Now we are moving to the next presenter, Dr. Nancy Soliman, is a postdoc fellow at MIT. She worked in concrete sustainability hub at MIT, developing concrete science engineering. Her PhD at University of Sherbrooke was devoted to develop ecological UHPC using waste glass of various particle size distribution. She had many awards from Canada, and she is a member of different ACI committees. Dr. Soliman will give us a talk as a representation of the work done at the CCH Hub of MIT about the development of electron conductive cement composites with self-heating capacity using nanocarbon black particle, a smart multifunctional concrete. And this work is co-authored with Professor Franz Olm from MIT. So please, Nancy.
Thank you so much, Ahmed, for introduction. Hello, everyone. I will start my presentation by saying that according to the United Nations forecast that by 2050, more than 2/3 of the world population will live in the urban area. So to meet this urbanization, we need more new infrastructure, and the building will be required, such as bridges, tunnels, high building, and road. But the concrete is the most used material in the world, as it has low cost material and strong material compared to the metal, foams, and the polymers, and highly resistant to the fire and the humidity and water compared to the wood, and also versatile, so it can cast at any shapes. And for example, in the United States, the annual production of concrete is about 10 million tons per year. But the question here, does the concrete meet social and environmental goals? The production of cement can contribute up to 8% of CO2 emissions, and also consume natural resources and energy consumption. Not only that, additionally, the traditional strength-only paradigm for structure design of concrete material is no longer adequate and has showed another two main flaws: and eco-efficient issues and durability issues related to the deterioration of the concrete within short term. For example, in USA, we spend up to $28 billion annually for structural rehabilitation and the bridges. And also, the second problem is functionality issues, as the traditional concrete cannot resilience in withstand loading condition or in the change in environment, as the normal concrete has no negative entropy input through matter or energy with external stimuli, such as motion, electrical, or chemical change. So my research question is how to produce innovative and multifunctional material for sustainable and resilient infrastructure to meet social and environmental goals. My research focuses in five main areas: developing innovative material byproduct using recycled material, functional material, nanomaterial, develop a novel technology to capture CO2 and the sequestration, smart and multifunctional material, structural health monitoring, self-healing, electron conductive and thermal properties, and enhancing mechanical and the durability of concrete in severe environment by developing ultra-high performance concrete. And using the collaboration and using the formulation and the lower carbon footprint using machine learning to pathway to achieving net zero 2050 goal. I will present here just only some of the part about smart and multifunctional material. And here I will present about the development of electron conductive cement-based material using nanocarbon particles through changing the microstructure of cement matrix. And here, when we adding a nanocarbon black into cement matrix, we develop a novel composite that has electrical conductive, self-healing, energy storage. And this is a patent between MIT and CNRS. But there is some challenge with using a nanocarbon black into cement matrix. The first challenge is dispersion, especially that the nanocarbon black is hydrophobic material and the cement is hydrophilic material. So how to disperse chemically and physically nanocarbon black into cement, and what is the effect in mechanical and electrical conductivity? Moving to the second question, how does the mixture proportion and the texture of cement matrix, such as water cement ratio nanocarbon black, can affect in the measurable electrical conductivity, Joule effect and electrical conductivity? The third question here, to get the full advantage of multifunctional material. So the question here, how does the origination of connected network volumetric wiring affect the mechanical and the microstructure of the composites? Here, I will present some of the results about the effect of the chemical dispersion of nanocarbon black particles. I'll present just only, we use several surfactants such as cellulose, polycarboxylate superplastizer, polynaphthalene, and synergy between both carboxylate and the cellulose and the polycarboxylate superplastizer. And here I will present the effect of polynaphthalene superplastizer as a dispersant agent in nanocarbon black particle. Here we use a constant water cement ratio 0.42 and the constant carbon content 12.5 per volume. And here we see that in the x-axis, like volume of the polynaphthalene superplastizer divided by the constant volume of nanocarbon black. In the right axis, here is the electrical conductivity, and in the left axis, this is the compressive strength. And obviously, when we don't have any dispersion, we found that the compressive strength of the material is reduced compared to the reference one, while we have achieved a good electrical conductivity. With adding more polynaphthalene superplastizer, we found that there is some slight enhance in the strength and slight enhance in electrical conductivity. 0.4% of polynaphthalene, we find a drop in electrical conductivity while a significant enhance in the strength. And this significant enhance in the strength due to that the carbon distributed in all over matrix, which lead to enhance the mechanical properties, while we lose the conductivity due to the breaking of the volumetric wiring of nanocarbon black particles. And because our goal is to achieve electrical conductive material, we recommended 4% of polynaphthalene superplastizer as the optimum percentage for dispersed carbon in cement matrix. So moving now to the second question about scalability. And here we this slide show the link between measurable electrical conductivity and the texture of highly heterogeneous insulator material. These paste and mortar were prepared using two different water cement ratio, 0.42 and 0.6, and the two different mortar, the weight of sand to the weight of cement 1:1 and 2:1. And what we see here that this figure show the tortuosity-based model performance, which shows a normalized electrical conductivity, measure electrical conductivity, normalized to electrical conductivity of pure nanocarbon black here, and versus nanocarbon black volume fraction, and modeling for that. For all the sample considered, and the inset of the model here is the performance in the log scale. And it can be observed here that the electrical conductivity of all cement-based and mortar collapse into the one curve, which concludes that the conductivity doesn't affect by water cement ratio or sand content. By the main parameter that affect in conductivity here is the carbon black, the volume fraction of carbon black. And also what we appears here that the electrical conductivity versus nanocarbon black volume fraction, like following the typical feature of percolation phenomena. This can be illustrated as the 4%. This is the percolation threshold, where the conductivity increases by order of magnitude. And at 15%, we saw this is the saturation point, where the conductivity increased by marginal increase in the electrical conductivity. And what we also found here from analogy with the diffusion problem, that we found that the electrical conductivity of the composite is driven by geometric tortuosity. So we found that the fine-tuning the volume carbon can be reached to the tortuosity value of 2. This means that this means that the path of electron takes only twice the length of the sample, and this is very important when designing the electrical conductivity in engineering scales. One of the most attractive applications of electrical conductivity is resistive heating capacity. And here we establish a fantastic relation between resistive heating capacity and volume fraction of nanocarbon black for different paste and mortar that produced with various water cement ratio and sand content. And here what we observed is that the Joule effect increased with addition of nanocarbon black while reduced with the sand addition. And this relation is so important when we design the material with resistive heating capacity, as the two quantifies materials that we should know here when we design our material, how much carbon should be added, and how much diluted this effect by addition of sand. Moving now to the third question about the effect of nanocarbon black in mechanical and microstructural properties, and using multi-scale engineering approach that we developed here at MIT. And here we use different water cement ratio going from 0.35 to 0.6 and different nanocarbon black volume fraction from 0 to 20. And we measure the conductivity, porosity, and the mechanical and the microstructural properties. By linking between the macroscale to microscale to nanoscale to have the full comprehension of the effect of nanocarbon black and cement matrix, at macroscale we measure the compressive strength, while moving at microscale we measure the hardness and indentation modulus using a micro indentation test, and fracture toughness using micro scratching test. Moving to the nanoscale, we measure the hardness and indentation modulus for low density CSH, high density CSH, the main constitute of the bonding agent in cement matrix. From the relation between hardness and the compressive strength, we can estimate the cohesion and the friction coefficient, the two parameters that define the strength of the material. From fracture toughness and hardness, we can estimate the fracture processing zone, and from indentation modulus and the fracture toughness, we can estimate the fracture energy. And using the micromechanics model, we can estimate the backing density of CSH. Here I am moving to present the effect of nanocarbon black in mechanical properties at microscale. And what we observed here, this is for the three different water cement ratio, 0.35 with the red line, and 0.42 with the blue, and 0.6 with the green, with the black. And what we observed here, that the addition of nanocarbon black volume fractions lead to a big reduction in the compressive strength. And what we observed is the second message here, that the reduction of the compressive strength at low water cement ratio is higher than high water cement ratio. For example, at 15% of nanocarbon black volume fraction, the reduction of the strength at water cement ratio 0.6 is about 25%, while the reduction in the compressive strength for water cement ratio 0.35, it was up to 60%. So moving now to the effect of nanocarbon black in the fracture properties. And the fracture properties here is the material property that describes the ability of the material to withstand in the presence of the crack. And it is very important parameter as represent the quality of the binder. By using the linear elastic fracture mechanics method that developed by Olm and the co-worker, we evaluate the energy release of the system, which represent the fracture toughness and the fracture energy. And this slide shows the three different water cement ratio, and water cement ratio 0.35 to water cement ratio 0.6. And what we observed here, that the addition of nanocarbon black lead to enhance the fracture toughness of the material, whatever the water cement ratio. And this reduction in the fracture toughness is originated from the crack deflections. So this crack deflection means that the crack doesn't go through the nanocarbon black inclusion, it goes around and above, requiring more energy to open the crack. So the nanocarbon black consider an obstacle in the front of the crack. And we, to confirm our result, we go the scan electron microscope, where we observed the fracture mechanism image of the scratch groove in the mixture that prepared with water cement ratio 0.6 and the nanocarbon black 15%. And what we observed here under scanning electron microscope, that the tortuosity non-planar geometry of the crack were clearly visible with the crack surface, which proves that this enhancement of the crack fracture toughness is resulted from the crack deflection. So moving now to see the effect of nanocarbon black in the ductility of cement matrix. And to quantify the ductility, we measure the ratio between indentation modulus over indentation hardness as a function of nanocarbon black in the left figure. And also we measure the fracture processing zone, which equal the fracture toughness divided by the hardness, which considers the far field stress in our test, and square it. And what we observed here, and this is fracture processing zone represent of the ductility, as if the fracture processing zone is so large, it means the material is ductile, while if the fracture processing zone is too small, it means the material is brittle. And what we observed here, that the addition of nanocarbon black lead to reduce the fracture toughness, the ductility of the material, where the indentation modulus over indentation hardness or the fracture processing zone. And this motivates us to eliminate the effect of nanocarbon black and link directly between the fracture processing zone and M and H ratio. And the results show here scales linearly with M and H, and the dashed line here, it represents the regression model with R squared 95 to 98%. And here the blue arrow shows the direction of increasing of nanocarbon black content. And this correlation shows that the plastic dissipation is reduced, and hence the fracture processing zone becomes smaller. And here we can say that the plastic dissipation capacity represents a reduction of the ductility when adding nanocarbon black. So this is a discussion question that we asked ourselves. Why does nanocarbon black addition lead to increase the fracture toughness, while lead to decrease the strength, compressive strength at microscale, and decrease the ductility of the materials? This is why we're moving to studying the friction and the cohesion of the material, the two parameters that define the strength. The friction estimated as a function between compressive strength at microscale, hardness at microscale, while the cohesion is estimated as a function between compressive strength and the friction coefficient. And what we observed here, that the addition of nanocarbon black for the three different water cement ratio lead to enhance the friction coefficient of the material. And this friction coefficient of the material resulted from the filling the capillary pore with nanocarbon black particles. And also what we observed is that there isn't any difference between the two water cement ratio 0.35 and 0.42. And this is confirmed that because the 0.35 is less than stoichiometric level, there is no more pore to accommodate with nanocarbon black particles. And here is to prove that the enhancement of the friction coefficient is resulted from filling the capillary pore by nanocarbon black particles. While we see a de-cohesion of the matrix when adding the nanocarbon black particles, and the friction enhancement is not large enough to compensate this de-cohesion, so the de-cohesion becomes dominant. And now we answer the last three questions. So why the compressive strength reduced, and why? Because this is due to the de-cohesion, and also why the ductility is reduced. This is due to also the de-cohesion, as the sole energy which is dissipated in plastic deformation is due to energy dissipation, only the de-cohesion. So friction doesn't have any dissipate energy. And why we have the enhancement of the fracture toughness? Due to the enhancement of the friction coefficient of the material. So this leads us to ask this question: what are the reasons of the de-cohesion of the material? And to answer this question, we go through to study the effect of nanocarbon black in the pore size distribution and the porosity of the material. And what we observed here that there is no any impact, the addition of nanocarbon black doesn't have any impact in the pore volume distribution or in the water or in the cumulative porosity. For the pore greater than 50 nanometer, which is the limitation of the mercury intrusion porosity. So now we need to understand what is the reason of microscopic de-cohesion. So this is why we are going to study the effect of nanocarbon black at nanoscale, where we show the effect of the backing density. This slide shows the effect of the backing density versus hardness in the left hand and the indentation modulus in the right hand. The backing density is very important parameter as represent for the nanoscale porosity of low density CSH and the high density CSH, the main constitute of bonding agent. And it can conclude from this relation that the addition of nanocarbon black lead to reduction in indentation hardness and the indentation modulus. And this reduction in indentation modulus and the indentation hardness resulted from the reduction in the backing density. And this reduction in the backing density resulted from due to the repulsive interaction force that developed between hydrophilic calcium silicate hydrate and the hydrophobic nanocarbon black phases. And this macroscopic de-cohesion resulted in the reduction in calcium silicate hydrate at nanoscale. And this shows a EGS for the electron conductive cement, which show that the carbon is like intermixes very well with the CSH, but the reason of the de-cohesion problem is the loosening of the backing density. From this, we can conclude this presentation that the dispersion can lead to multi-scale optimization of nanocarbon black. At low dispersion, we can achieve at multifunctional material, high conductivity, normal strength. While at high dispersion, we can break the conductivity between nanocarbon black particles, but we can obtain high strength materials. Also, it is possible to upscale conductivity and resistive heating from the paste to the mortar. And what we observed is that electrical conductivity and resistive heating of the material increases with increasing nanocarbon black content. Electrical conductivity does not depend on water cement ratio, sand content, or any material. And the sand inclusion dilute the Joule effect. The fantastic conclusion that from the multi-scale engineering approach that we linking between the micro to micro scale, which give us the full comprehension of the effect of the material, that we figure out that the addition of nanocarbon black lead to the two phenomena: friction enhancement at micro scale due to the presence of nanocarbon black at larger pores, and this friction enhancement that resulted in the enhancement of the fracture toughness and of material. While the addition of nanocarbon black leads to the de-cohesion at nanoscale, de-cohesion of the material, and this de-cohesion of the material results from a reduction of backing density of calcium silicate hydrate at nanoscale. And this de-cohesion is the reason for the reducing the compressive strength at microscale and reduction in the ductility. So what is the application of nanocarbon black? By application of nanocarbon black, we can use it for the de-ice pavement without any root salt, which root salt it has a very bad impact in the contaminated water and the concrete deterioration. So, and also we're saving $1 million of repair and operation system, and we save a lot of multi injuries that causes by snow. So thank you so much. So any question?
Yeah, Ahmed, I think you're muted.
I believe Ahmed, yeah. So if anyone have any question, so I'm gonna ask myself, or can Professor Julie?
No, I have actually typed a question. So if should I ask it?
Yeah, sure, yeah.
Go ahead. Yeah.
Okay, so Nancy is, is very nice presentations, no doubt about it. It's a very nice work. What I was saying that to get this percolation threshold with this, nanocarbon blacks, do you think you will require much higher dosage of nanocarbon black to achieve the desirable multifunctionality that you are looking for, which as opposed of might be affecting the other properties of the concrete? Because your percolation threshold you mentioned is above 4% or something. Can you explain
4%.
this?
Yeah.
Yeah.
So actually the percolation threshold at 4%, it is very low compared to this is like doesn't have any nanocarbon black doesn't have any aspect ratio, but unfortunately that we lose the strength at microscale, and to have a full advantage of multifunctional material. Now we are understanding that the reduction in the strength due to the de-cohesion of the material, and by that we can adding some bonding agent or adding some functionality to the carbon black particle, which enhance the bonding between nanocarbon black and the matrix without losing the connection between the particles.
So which ratio at this moment you are working with that you have the desirable, the electrical conductive effect, the Joule effect that can warm up the concrete uniformly, you are suggesting?
I can say maybe at from 8 to 12%, you will have the good conductivity, good resistive heating, and also acceptable strength. But beyond 15%, we have a big reduction in the strength.
Yeah, that's what I was, okay. On your slide 18, have you been, wasn't clear, have you been mentioning that you don't have any effect on the porosity distribution?
Yeah, I think nanocarbon black doesn't have effect in the porosity for each family. For example, for water cement ratio 0.6, we don't see any significant impact in the reduction of porosity. So the porosity from 30 to 34. So because this is like, which confirm that the reduction or the de-cohesion in the matrix come from nanoscale.
I see. Interesting. Thanks a lot.
Thank you so much.
Great.
So,
I can combine two questions into one. So why nanocarbon black? And also, what's the corrosion challenge in the long term?
Why nanocarbon black? Nanocarbon black is the cheapest material, and also it is compared to the nanocarbon tube or compared to the steel fiber or carbon fiber. But what is the effect in the corrosion? Actually, we don't know exactly what is the effect in the corrosion, as it's still like at the beginning of the research. But so this is why I don't have the accurate answer for that. Especially that it has a big reduction in the strength. So I don't know exactly what is the effect on the durability.
Thank you, Nancy.
Thank you so much.
Thanks a lot, Nancy.
Thank you so much. So